Welcome to a course on calculus differentiation and RS integration. In this lecture, we will begin with the basics for Riemann-Stieltjes integration. Let us start it. Okay, let us write the Riemann-Stieltjes integration. This is the topic of our talk, and we will start with the definition of a partition. So, partition. This is the thing that we define for a closed interval AB. So let this be a given interval, a partition. So partition for what? A partition P of the interval AB means a finite set of points. X0, x1, etc. till xn, where this satisfies some relation, that is your A is x0 and this has to be smaller than or equals x1 smaller than or equals x2 and it goes till xn which is equals b, and here we write delta xi to be xi minus xi minus 1, where I runs from 1 to n. Okay, we have written this as a mathematical definition, but what does it actually mean? We are considering a closed interval, right? So if you consider this as your interval, you will have to choose some intermediate points between this a and b. So this a is taken as x0 and this b is taken as xn. In between you can choose several points. Okay, there is no restriction upon it. You may choose points as you like. They need not be equally interval. They have not specified anything like this. If this is my x1, I may choose my x2 very close to it. This may be my x3, this may be my x4, this may be my x5, this may be my x6, x7, and in this way we'll have to choose n points, right? Only the collection of these points we call it as a partition of the interval AB, right? Once we define a partition, once we know the partition of an interval, then we may define Riemann integral. Okay, so basically integration is what? Integration is the process of summing things up, that is the process of adding. Okay, what kind of things that we sum up to get an integral, that is what we will see. Okay, the notion of this integral, the ideology behind the integration was initially developed by Riemann, and that is why it is known as Riemann integral. After Riemann, there were so many people who contributed to the theory of integral calculus, and we have two types of integration, namely Riemann integration and Lebesgue integration. Primarily, we deal with Riemann integration, and Lebesgue integration is out of our scope, that we will not discuss in our course. Right? Okay, let us define it mathematically. Suppose a function is given which is a bounded real function which is defined on the interval AB, right? Now corresponding to each partition P of AB, we write mi to be the supremum of f of x, where xi minus 1 less than or equals x less than xi, and small mi to represent the infimum of f of x over the same thing. Okay, here if you closely look at the things, you may notice that given f is a fixed bounded real valued function which is defined on the interval AB corresponding to each partition P, which means for the same interval you can take as many partitions as you want, and to each partition P we define big mi and small mi in this fashion, right? And the notation UP of F is the summation I runs from 1 to n mi times of mi multiplied with delta xi, and this LPF is called as summation I runs from 1 to n small mi delta xi. Here these two are called as Riemann sums. Okay, together they are called as Riemann sums. And if you have to look at it, if we have to give the individual names, it is known as that UP of F is known as upper Riemann sum, and later that is LP of F is called as lower Riemann sums. Okay, here that is something in general that let me write it in another color. Upper Riemann sum and lower Riemann sum of the function F with respect to the partition P. So to this partition, this is the upper Riemann sum and this is the lower Riemann sum. In a similar way, if you take another partition, for that also you are able to find out another upper Riemann sum and another lower Riemann sum. Okay, and with this we define upper Riemann integral and lower Riemann integral. That is, and finally we represent that integral a to b with an upper thing f of x dx is going to be the infimum of UPF, and integral with lower bar a to b f of x dx is the supremum of LPF. Here the infimum and supremum are taken over all possible partitions of the interval a comma b. Right? The integral sign, this notation was introduced by Leibniz. Here the Riemann case, hope you people have remembered something from your school days, that is we have studied two types of, in our schooling days we dealt with two types of integrals, namely definite integral and indefinite integrals. Riemann integrals are subject to definite integrals, right? The of course we will have limits, right? So this is the upper Riemann integral and this is the lower Riemann integral. Let us mark them as equation 1 and 2. Generally, this upper integral and lower integral need not be equal. When these two things are equal, we say that the function is Riemann integrable over the given limit, that is over the given interval, and is denoted as integral a to b f of x dx. Now I would like to remark something. First one, if f is Riemann integrable, then we write f is a member of script R. So this letter is used to denote the set of all Riemann integrable functions, right? And this UPF and LPF, they are numbers, okay? They are some, finally they land in some numbers. The numbers UPF and LPF forms a bounded set, And from the construction of UPF and LPF itself, you might have noticed that this consists of the minimum values, that is the infimum values, and this consists of the supremum values. Hence, your LPF is always smaller than or equals UPF. This tells you your lower integral, okay, your lower integral of any function over the specified interval is smaller than or equals the upper integral of the same, right? So this is the ideologies about Riemann integrals. Now we are going to Riemann's Stelz's integral, and that is sometimes abbreviated as RS integral. In order to define RS integral, the things that we need is a monotonic increasing function. So let alpha be a function which is monotonically increasing, on the interval AB. Okay. Now here also you can find the partition and all those things are there, right? Corresponding to each partition P of the interval AB, we write delta alpha I to be alpha of xi minus alpha of xi minus 1, right? It is given that alpha is a monotonically increasing function. So if it has to, okay, from this let us see something. It is monotonically increasing, which means, you know, from this interval itself you know that your A is smaller than or equals B, which means your alpha of A will be smaller than or equals alpha of B, and this alpha of A and alpha of B has to be finite values. Therefore, your alpha is bounded in this A comma B. Okay, you will have to remember these things in mind, and hope you know what do we mean by a partition. So with any partition B, we shall write things in this fashion, right? Once we write these things, it is clearly your okay. Here, since xi is bigger than or equals xi minus 1, your alpha of xi is bigger than or equals alpha of xi minus 1. This tells you that your delta alpha I is non-negative. Okay. Now, for sorry, for any real function f which is bounded on the given interval AB, we shall write UPF alpha to be the summation I runs from 1 to n mi delta alpha I, where your mi is supremum of f of x, where x can be any point in the subinterval xi minus 1 comma xi, and LPF alpha to be the summation I runs from 1 to n small mi delta alpha I, where your small mi is infimum of f of x over the subinterval xi minus 1 comma xi. And we are just repeating the same ideas. So your upper Riemann Stelz's integral is f of x d alpha is infimum of UPF alpha. This infimum is taken over all possible partitions of the interval a comma b, and your lower Riemann integral is the supremum over all possible partitions of lower sum. Right? Here also the same ideologies. If your lower and upper Riemann Stieltjes integrals are equal, then Fs Rs integrable, we write integral a to b f of x d alpha. Okay, here let us remark, if Fs Rs integrable, so in order to be Rs integrable, we rely on some monotonically increasing function alpha. Therefore, we write f as a member of script r of alpha. Okay, in your Riemann Stieltjes integrable, that is Rs integrable class of functions, if you take alpha of x to be x, that is if you take the identity function, then your Riemann Stieltjes integrable functions becomes Riemann integrable functions. Okay, thank you.